and he's going to give an overview of quantum computing. So yes, whenever you want to start, please go ahead.
Okay, thank you. Thank you for the organizers for giving me an opportunity to talk. So I was asked to talk more general about quantum computing. So I'm giving my view of quantum computing more than the broadest sense that I can give you. But my focus really is on figuring out how we can advance physical sciences, which is nuclear physics to chemistry to whatever you can think of, on near-term quantum computers. So the perspective will be a little bit from that direction. Okay, come on. So, of course, the mandatory slide as to why do we even care about quantum computing is very simple. And I kind of made two of these bullets the largest, and that is the speed-ups over classical computing, which is, I think, very important for all of us when we are trying to do simulations to try to simulate our physical processes, which is also another way of looking at it is quantum simulation. Quantum simulation here is a little bit different in that sense because it's more aligned with Feynman's interpretation, where he was thinking about actually using a quantum computer to model a quantum system. Of course, there is other good reasons to use quantum computers, encryption, and what seems to be a very big field right now to try and figure out is the development of efficient optimization algorithms for like traveling salesman's problems and logistics problems that are out there. So what's interesting in quantum computing is that it's really a very early stage technology still. We are familiar with our classical computers. We have, well, for the longest time, we had x86 chips in different flavors, but they all had very similar behaviors. Now we've seen FPGAs more come online and GPUs, which are slightly different, but fundamentally still the same technology. But if you look at quantum computing, we're really still in that early stage where lots of technologies are being explored. We can go from solid state to ions to atoms to superconducting. Of course, everybody heard about the challenges when it comes to Majorana, quasi-particles. If you really look at where the technology is right now, those that are the furthest ahead are the ions, or better said, the trapped ions, and the superconducting qubits, although others are becoming more and more relevant. I put down here also D-Wave as a quantum computing technology. There has always been a debate if that's truly quantum computing. Interestingly, now D-Wave is also moving towards developing more traditional superconducting qubits for their system. So they're kind of sticking to that bandwagon in the long run. And that is what's really interesting for us from a scientific point of view is that one, this is still a physics problem that needs to be solved. But on the other hand, there is a large number of companies that are being involved. So that means there is actually money, funding to move this field forward. And that is not always the case. So it's actually a kind of brings together a disparate set of fields and actually trying to move this field forward, both from academia all the way to industry. But there are still many, many challenges when it comes to quantum computing hardware. One of them is simply we don't have enough good qubits to really get a quantum advantage. Now, everybody has heard the 50 to 100 qubit systems that are being announced and demonstrated, but those are not what I would consider good qubits. So what do I mean by that? Their coherence, I better said, the available computer time that you have is very short, tens of seconds for trapped ions, hundreds of milliseconds maybe for superconducting or others. But it effectively boils down to, if you really want to run a quantum computer, you can do tens to hundreds of operations before your answer becomes useless. And that comes simply because noise is still pretty large. What's also an interesting challenge, and people don't realize that all the time, is that each technology actually comes with its own operating system instruction set, which is very different. It has different gate sets, and there's different operations that are being used. This merger has happened already, happened a long time ago in classical computing, and will eventually get more uniform when it comes to quantum computing too. And as a result, also, software tools and compilers are still in their infancy. There's still a lot of work that has to be done to really provide a user, a physicist, a chemist with a software suite that allows them to take a scientific problem, code it up, and say, go run. So I'll give you an example for gate sets, and here's some ideas that are there. So each chip has, for example, they have the single qubit rotation. Most of them have sort of usual rotations in Hadamard's, but a 2-qubit operation could be a CNOT, a CC, it could be a CXX, it could be a swap gate, it could be lots of different ones. And they're all optimized slightly differently. They all prefer a 2-qubit operation, which is the most important one, in a different way. What's even more interesting is that a lot of chip technologies have constrained topologies, especially when it comes to superconducting qubits. When it comes to trapped ions, because actually moving ions is not that big of a deal, there is a lot less constraints on the topology of the chips. So you really need compilers, you really need tools to translate the gate sets, do the mapping, do this in the most efficient way, because if you actually need to move qubits around, it requires a lot of 2-qubit operations, which are very noisy at this point in time. So if you look at the field and when they're actually doing quantum computing, how do you make quantum simulations feasible on this hardware? Has been a game of really reducing the requirements to run quantum simulations. So there is a lot of work that is being done in the literature on minimizing the number of qubits you actually have to use. So how do I efficiently encode a problem? How do I do this in the most smart way? And how can I reduce the depth of the circuit? Or better said, reduce the number of operations that I have to do to get an answer. So for example, for the second one, there's a lot of work that's being done on developing localized Hamiltonians, trying to reduce the number of interactions, reduce the level of entanglement, change the picture that you're using, qubitization. There's a lot of technology that's being used and a lot of algorithms that are being developed to enable this. Now, of course, if you're having a truly strongly correlated system, the question is how far you can reduce the interactions. Because if everything interacts with everything, of course, it's very hard to do this. So most of the strategies are not only using localized Hamiltonians, but effectively have also more localized problems that they're trying to solve. Of course, there's a completely different strategy, and that is using error mitigation strategies. And I say error mitigation in the broadest sense. This includes error correction. But error correction, if you're talked too much about that, the Department of Defense does not get very happy with you. So we use generally the term error mitigation for kind of all ways to correct. One of the challenges with error mitigation is instead of having a fixed set of qubits that you can do your simulations on, you need many orders of magnitude more qubits to actually encode your error mitigation strategies. So how do we get to useful quantum computing for science? Because that's, if you look at all of us, that's what we're after. We really see that there is a two-way street here coming from the hardware technology, the physicists developing the qubits, where they are able to increase the number of qubits that are available. They're working on increased lifetimes, i.e. we can do more and more operations and increasing fidelity and thereby reducing errors. Will they be able to get to something that is of the order of what you would see on a classical computer, that would be a hard sell, I think, because of the sensitivity and the interactions that quantum systems will have with anything that isn't close to them. So there is more work that can be done on the scientific algorithms and software side too. Again, I mentioned already reducing the qubit count, find ways to decrease the operational counts. But there's also a lot of effort nowadays in incorporating error resiliency. People are looking at ways to do error mitigation, error correction in the most efficient way without doing full-blown error correction and going and requiring huge numbers of qubits. And it's actually a real interaction between those two, because there is a balance. You increase your qubit counts, you lower your topology and interactions. So you actually have to also account for the lower topologies at that point in time. But interestingly, we can actually do interesting simulations already. They're small scale, but we can actually do fun stuff. So this is some work that I did with the high energy physics group at Berkeley lab. When they started to get interested in quantum computing, one of the first problems we looked at is actually Parton showers and effectively interfering trees. So we were able to code up a very small problem, which is a few qubits of two fermions interacting with a scalar boson, trying to count kind of the interactions, which led to, I would say, a pretty complicated bookkeeping algorithm that we eventually simplified for a problem where we limited the amount of scalar interaction that could happen. But what's interesting is that using this algorithm and actually doing this on a quantum computer, you can actually show that quantum interactions, which G is driving here, are actually important. And we are able to show that on a real quantum computer. Are they correct? So the red boxes are a numerical simulation on a quantum simulator. The triangles are the real experiments. Are they exact? No, but we do see the physics that we need to see out of a quantum computer. So it is feasible to at least start probing some small problems that realistically you could do on a classical computer too. But it's important to do these kind of experiments because one, you learn about what algorithms would actually work, what the challenges are with these algorithms, and where the issues are, especially when it comes to dealing with noise, for example. So when it comes to algorithms, if you really look at literature, the two most common algorithms for quantum simulations are these two, which is quantum phase estimation and the more recent variational quantum eigensolver. They both have their pros and cons, and both of them are kind of the building blocks for many other algorithms that came as a result from that. So the phase estimation is a challenge right now because it simply requires a large number of operations to prepare a qubit, to evolve, and then do a quantum Fourier transform to find eigenvectors and eigenvalues. But it is, in the long run, the most likely algorithm to be able to do the science that we want to do. To reduce the number of operations that are needed, comes out of effectively Jasper-Guzek group. They decided to actually do an algorithm where they only prepare a measure and do the rest classically. What that means is effectively they measure the state on a quantum computer and then combine the eigenvalues coming out of the quantum computer with classically computed values, and then minimize this equation or minimize the energy that this Hamiltonian can have. So it requires you to do a classical eigensolver, a classical optimizer in combination with these prepare and measure operations. Now that's an interesting problem on its own. And there is an enormous amount of literature, especially in the last couple of years, figuring out how to do this for large numbers of parameters. So every time you have one of these parameters of your wave function, So you have to parameterize your wave function to actually compute these eigenvalues here, these averages. What's interesting is that the more complex you make your wave function encoding effectively, the more complex you make your ansatz, as they call it, the harder it becomes to optimize. And now, effectively, the classical optimization might become an NP-hard problem to solve. So you're back to square one. So there's a lot of literature lately on barren plateaus, for example, where you kind of have very flat optimization surfaces that cannot be really moved further. So some of the work that we did early on, when we were looking at actually the variation quantum eigensolver, one of the things that bugged me is that it was really designed initially to do the ground state. And when we, as chemists, so I'm a computational chemist by training, are looking at physical problems, we're often not interested in a ground state. So we actually chose an alternative approach where we did effectively a linear response on top of the subspace, on the top of the VQE that we had, and then effectively defined a generalized eigenvalue problem that is small, that can be solved on a classical machine, that allowed us to have access to the excited states, and as a result, also other properties. Turned out that that worked out pretty well, and I didn't put a slide in where we showed that early on that it works on the hardware. We took that actually a little further and looked at some larger active spaces on a real quantum computer. So this is more recent work by my postdoc, Miro Urbanek, who is now at Atom Computing, where he actually looked at the excited states for not just smallest molecule, but also for some other molecules, and then realized also a very big problem, and that is these eigensolver problems here. These problems, we need to measure overlaps, we need to measure the wave function. Actually, we need to measure the Hamiltonian matrix elements and the overlap matrix elements, but there is no guarantee that those are, for example, positive definite. So it required actually a bunch of applied mathematicians to start looking at how we can kind of clean up our eigensolver problem to actually get reliable results. In the end, you can actually get pretty reliable results, as you can see from this. But again, these are very small problems. You're talking about a few qubits only. So we started to build on QSE2. And effectively, if you think about this, what we're trying to get is a set of eigenvectors, and how we encode that could be done in different ways. So in the original plan, quantum subspace expansion, we just take excitations out of the ground state. But why do you actually have to take excitations out of the ground state? You could do also a real-time evolution from any some state. So that's what we did in this work more recently, where we just take a state and just evolve it with real-time, evolve it with the Hamiltonian. This gives us a bunch of eigenstates that we can do pretty much the same thing. We can get a generalized eigenvalue problem and solve the ground state and excited states. Effectively, what it boils down to with these kind of methods, we're trying to find a representation of the Hilbert space that covers the essential components of the states that we want, and then do a linear, well, we diagonalize effectively that matrix, and then we get the correct eigenstates that come with the Hamiltonian. What was interesting when we started to do this is that we can actually translate the original generalized eigenvalue problem into something that looks more like a unitary form that we want to use on a quantum computer. It turned out that when we looked at it very carefully, that these things are nothing more than autocorrelation functions that have a very clear, clean tuplet structure. So which means that rows shifted rows are pretty much the same. This allowed us to actually also get to a structure where we can avoid the computation of the Hamiltonian matrix elements. We only needed the overlap matrix elements, and only for a subset because they are having a structure that we can take advantage of. And we only needed to do a linear number of measurements instead of quadratic. So what we were able to do is actually do these kinds of simulations up to 6 qubits and actually get very accurate eigenstates, not just the ground state, but also higher states of the Hamiltonian at a very low measurement cost and also a low computational cost. There is a price here, and that is you need to figure out a phase factor. So you actually need to do a Hadamard test, which requires a controlled operation that makes these circuits a little deeper. So we cannot go too far yet, simply because, again, our circuits are going to get deeper. Now, that's all about systems that we know a well-defined Hamiltonian of. But really, if you look at what science wants to do, most of us want to do systems that are really embedded in an environment. So we really want to deal with open quantum systems. So we want to be able to simulate a model that is interacting with an environment. There's a lot of challenges with this to do this physically, right? So my postdoc, McKenna Metcalf, worked really on this for a couple of years with the real question: can we engineer quantum simulations to generate thermal states for arbitrary systems? So our latest advance is that we are actually having a very nice set of algorithms that allow us to do exactly this. We can do dissipated dynamics on quantum computers, and it allows us to really sample Boltzmann distributions and really study these kinds of systems. So what was interesting coming out of this is that kind of drew the attention of some of our new co-workers, which is Jarzynski, who is on here, Felix Ringer, Matthias Ploskon, James Mulligan. They're in the nuclear physics division. I don't think it's a division in LBL. And they have been interested in looking at open quantum systems and heavy ion collisions. So we did some work with that, actually trying to simulate some of these systems on quantum computers. And what we did here is kind of model a two-level system, which probably is something like a quark-antiquark pair interacting with a quark gluon plasma. And then we were able to just tune the interaction strength. What you see on the left here is kind of a circuit for one cycle in the optimization step. You can see that these circuits, these number of operations become large. It's 1, 2, 3, 4, 5. You can do the math. And then you need to do multiple cycles, many cycles in some cases. But they're able to show the interaction having an effect and getting you close to the thermal limit. And then being able to do some of these on real hardware, where we can actually show pretty decent results. What's interesting, and you see all these terminologies here, readout corrected and rim corrected. What's clear in any way, shape, or form is that you have to do error correction or error mitigation to get reasonable answers out of a quantum computer. And that continues with a follow-up that is on archive right now, where we actually did some non-equilibrium dynamics and thermalization. And here we chose a very simple Schwinger model, where we effectively have fermion sites that can be occupied by electrons, positrons that interact via an electric field, and then have interactions with the environment. What we did here is actually do the simplest one and take this little piece here up front and take 2 fermion sites and one qubit to representing the environment. So if you look at that from a quantum system problem, we have 2 qubits for the environment, And all of a sudden, if you really look carefully, you see, oh, wow, I have 4 ancillas representing the environment. I thought you said 1. Well, this experiment was done before we could actually do something that is needed with these kinds of algorithms, and that is a reset of the environment qubit. This hasn't been available for a long time, so the approach has been taken to just put a new qubit in to represent the environment in the next cycle. Now I have to say that the latest editions of quantum computing systems do allow this quantum mid-circuit reset. IBM has it now, Honeywell, and most of the systems will have this now. It is a challenging technology to do resets because a reset generally takes a lot of time. So to get it into the 0 state. So it is able, the quantum computers are able to do this now. But with even this simple an algorithm, we can get results that match really well with the numerical simulations, both from a simple Runge cutout to actually doing a simulation of the algorithm itself on a quantum computer. Then there is one other property that is very much of interest, and at least for us, and that's computing concept of free energy. Let's say you have a system that is in state A and you want to see what it takes to move a system from one state to another. You can think of something that is in a ground state that you want to get into a terminal state. You want to slowly turn on an interaction. So there's a lot of work in the literature in general about free energies, where we effectively look at things like second law of thermodynamics, which we can actually then look at a work as being a approximation to the free energy, which we can actually get from a Jarzynski equality equation. So the challenges here, of course, is you need to prepare a state and then measure the work over a trajectory. But of course, because this is statistics, you have to do a large number of trajectories. These are not trivial type of algorithms, but my postdocs, Lindsay Bassman and Katie Klimko, were actually able to really work through an algorithm that works, where they prepare an initial state using the quantum imaginary time evolution. They get do a match measurement. Effectively, they get minimally entangled typical thermal states out of that, that they can then use in many different ways to get initial energies and final energies. And what they have to do is effectively a lot of cycles to get a lot of different trajectories and get results. They're able to do this pretty decently. But again, as you can see, raw QPU in this, error mitigated. You definitely, even in these small systems, have to do error mitigation. They have done bigger systems now, up to 5-6 qubits, but we can actually use these algorithms to compute the free energy of a material system where we slowly turn on a coupling interaction. So let me switch a little bit to, that was kind of science and algorithms, switch a little bit to programming a quantum computer because, okay, we are used to our programming models right now. We have our Fortran compilers, we have our Fortran languages, C++ languages, whatever we can think of, Python, and many others. But if you look at the programming environment right now, when it comes to a quantum computer, it's a lot lower level still. You're effectively programming a computer like you would be doing a classical computer 30, 40, 50 years ago. So it is not a high-level programming language yet. So there's a lot of work that has to be done to develop a complete programming stack on a quantum computer. Because we as scientists would want to define a problem, maybe think about algorithms in the sense of a circuit, but really should we be thinking about a circuit, because that is something that a compiler should be doing for us. So the compiler eventually has to translate it to a processor. But the challenge here again is these optimizations of these and minimizations of these circuits or operations is also a challenge that becomes an NP-hard problem. It's also a quantum complex problem in the long way. But that's not all the end. When we actually run on a quantum computer, we're not running an Hadamard. We're actually running a bunch of pulses. So we also need to translate even these operations into hardware, into pulse shapes. And of course, hardware, because of its noise, we need to tune these pulse states all the time. There is a lot of work nowadays to try and kind of build a bridge here and actually think of compiling a quantum algorithm directly into pulses instead of through an intermediate step, because that's where we need to go in the long run. But it's kind of gets you back to what we're trying to model is a scientific problem with pulses that kind of also is a physics problem. So again, we're trying to solve a physics problem with a physics problem. So if you look at software that's out there, every company that is building a quantum computer will have their own software stack. And this is no different than what we see on our cell phones. Everybody has a different type of company cell phone. They will have a different operating system. So these are the most common ones. Qiskit for IBM, of course, Google Circ. And then Xanadu has come really up with their Strawberry Fields. So those are kind of more total compiler programs. There is also a lot of effort that is being put forward on things like compilers. SpyTicket is a compiler that is integrated with some of these. QTIP is a simulator. There is lots of effort actually when it comes to simulators to run them on high performance computing platforms. There is multiple that are available to run on tens of thousands of CPUs. And only those can simulate 40, 50 qubits. So some work that we have done in my project, which is called AIDE-QC, is to develop a kind of a programming model that is based on a quantum JIT, so just-in-time compiler, where we use an underlying framework called QCore, where you can actually code your program as you would think of running and writing in a classical sense. So you can map your C++ code. You can also do this in Python. So I would say we have both a C++ and Python, which is really where we want to go. We want to be able to write our equations in a quantum-ish way, but we want to define our physics. And then we want to just say, very simply, go run. This is really where we want to go eventually when it comes to our software stack, is to be able to develop our problems, our scientific problems in a high-level language, and then have the compiler and software suite underneath deal with all the issues that have to do with actually running it on a quantum computer. Now, of course, I mentioned many times already, there is still a lot of errors. So there is a lot of tuning that is being done. So doing this all automated is still a challenge, but we're also building in error mitigation strategies to actually incorporate it in this kind of a workflow and be able to make it easier for users to develop computational simulations. So there's a lot of different things that can be done. We are also looking at circuit synthesis in this language, so we can actually do new kind of operations, and we can leverage a lot of things like NumPy to do this in a most efficient way. But then, okay, we have a programming language. Now we actually have to get optimal circuits. Before I do that, so this is an example of that programming model, is where we actually did something that looks like a material system simulation, where we can just tune the parameters and actually do a simulation just using this high-level framework. What happened is actually we developed, this is what's called the Quasimo library. It's actually a library on top of what you just saw with that just-in-time compiler. So we developed kind of a high-level programming language on top of the infrastructure that we have. And what we're doing is actually building multiple kind of renditions of this higher level programming language, which is more like a physics specific programming language that you can then use on a quantum computer. But the real problem then becomes compiling. And how do you get your shortest circuit, shortest number of operations? And that's general synthesis problem is truly an exponentially hard problem. How do you get, for example, from a unitary to a circuit? There's a lot of work where users develop their circuits and then codes like PyTicket use symbolic manipulation to optimize that. There is a lot more gain to be made if you really look at the unitary and try to discover the most optimal circuit out of this. It is hard, and what we've been doing, and this is called the Berkeley Quantum Synthesis Toolkit, is develop multiple different compilers that allow us to do different scales of problems and at different speeds. And again, this is expensive, and for the large scale problems, we definitely need supercomputers to even get effective circuits. But we've been able to get a very good sets of circuits out of this. Generally, we get a 6x reduction in the number of operations that we have to do. So that is actually a big advantage because it allows us to actually do larger and larger types of problems. One of the things that came out of actually this work, QFast, is that Lindsay Bassman, my postdoc, was generating circuits for, in this case, what's called free fermion systems, and found constant depth circuits for dynamic simulations on quantum computers. Effectively, free fermion Hamiltonians are fast forwardable, and you can actually generate very efficient circuits that are only that are constant in depth and have a very fixed, well-defined structure that we can use. Why is this important? Is that we can actually run extremely long time simulations now for these kinds of models and run them at constant depth and get very accurate results. Well, if we want to really do the other way, where our circuits are growing over time when we do more time steps, then all of a sudden we get very poor results because we just accumulate too much noise. Our latest in this is actually what's called Quest. So we've taken another step where we can not only optimize the circuits in the most optimal way, we can also think about approximations. Do we really want to solve the unitary or want to solve the Hamiltonian exactly? Can we get away with some approximations to this? What we've been able to show is that depending on how far you're willing to take an approximation, again, most of us, we do not want the exact answer. We want to have an exact answer within a certain error bound. So if we can get actually within the error bound, but not exactly solve the unitary or solve the Hamiltonian problem, we would be able to do larger simulations again. So what we've been able to show is that we can actually do this for systems that are up to 128 qubits, and we can get anywhere from 30 to 80% depth reduction. Why is there such a big range of 30 to 80%? Well, if you really look at some of these Hamiltonians, some of them are more local in structure than others. So the more local they are in structure, we will actually find that with these kind of robust approximations. The price of this algorithm is that we have to do more measurements, but that is a small price to pay because as you see here in the middle, we see a significant reduction in some of these problems. For example, so the TFAM is one of those free fermion problems we know we can do in constant depth, but the full Heisenberg, which is not a free fermion model, has a baseline circuit of 900 CNOTs, but we can reduce them to 11 C0 by allowing some level of approximation. And if you then compare them to the experiments, we still get very good results relative to the ground truth. So what you get effectively here is a balance. If we approximate the Hamiltonian a little bit, we can get shorter circuits and get more reliable results out of it. Do we not do the approximation, we accumulate more noise and we also lose accuracy. So it's a balance into where we put the approximation and where we allow the errors to accumulate. So to say a little bit here, so the AIDE-QC software stack that I mentioned is available. You can actually download it. It has binary installs for multiple platforms. And we have developed a pretty extensive user and developer guides with lots of examples that you can work through. Then finally, I want to briefly talk about Qubit errors. So errors really come through two ways: relaxation and decoherence. If you really think about it, relaxation, dampening, which is driven by the environment, really decays a state from 1 to 0, while dephasing is really smearing the energy levels in a way that it changes the phase of the system. So effectively, your phase becomes less precise. Being able to model this and dealing with this is a challenge that people have been working on for a long time. And I'll go and do this one in a more simple way. If you really look at where we are in the error regime that is kind of in the red, 10 to the minus 2 kind of regime. And I think in the near future, we can get maybe to 10 to the minus 4. But if you really look at where we are in classical computing, we do 10 to the minus 16 and better. Realistically, I think we can get away with 10 to the minus 14, probably for quantum algorithms. So there is a big gap still between where we think hardware can be and where we really want to be. And this is where then fault tolerance and error correction comes in. And I want to stress again, quantum computing right now is still a physics experiment. It's the physicists developing the next generation technologies. We're not at an engineering point of view yet. Noise is everywhere, and we need to measure errors. One of the errors is readout errors. So most of the things that were being used in the initial work was as thinking about inversion approaches. But when we were talking to our high energy physics colleagues, specifically Ben Nachman, he was like, well, we do this all the time in high energy physics at CERN. So they have, of course, more regularized inversion approaches. And these are more stable in the way they actually can do their calculations and get readout corrections for our simulations. You can also, as I mentioned, build an error correction. The price of an error correction is an increase in qubits. So this example here, for example, required 6 qubits to look at a 2-qubit problem and be able to do a single error detection and do some magic state preparation. Still though, using this, we can actually get results that are pretty accurate. Still not as accurate as we want, because there is higher order 2-qubit errors or higher errors that we did not capture. But we're able to use this to actually get drastically improved results on quantum computers. So you have the readout done, you can do error correction, but error correction gets very expensive. If you think of through error correction, if you have one logical qubit that is error corrected, you might need thousands, maybe tens of thousands of qubits. So there's other ways that people have been developing error correction or error mitigation. One of the most popular ones is the extrapolation approach, where we purposely increase the noise and then extrapolate to what a zero noise would be. And another approach is to really deal with coherent noise. So biases, can we actually randomize those? And then effectively, when you look at it, randomize them towards the average result being a correct one. So these kind of techniques are used pretty much widely now in quantum computing. What's interesting when it comes to the linear extrapolation, some work that comes out of the high energy physics group, is that there has been some issues with the linear extrapolation because you have to do huge numbers of operations again. So what they developed is a approach called RIM, where you can actually do fewer identities and use polynomial fits to still extrapolate to the zero noise. There's actually a bunch of papers, and there's another one now on archive, but they can actually use few additions of C0 identities effectively to develop an extrapolation scheme to get you to zero noise. And we actually use this. So this is our, I would say, highlight of a very recent work that got in PRL, where we used all these techniques together. We used readout correction. We used randomized compiling to mitigate these coherent errors. We used noise correction. And so we developed another technique called noise estimation circuits, where we can actually effectively figure out how things decohere over time and correct for that, and then use this extrapolation scheme. But what is nice about this work is we're able to get this original circuit, which does not even closely resemble what's exact. You almost have a random circuit here. But what we're able to do with all of these techniques is to tease out the right answer out of this information. What it all boiled down to is that we're able to run circuits and operations up to 220 C0 operations on top of all 1 qubit operations. So we can run circuits that are many hundreds of operations and many of entanglement gates and get reliable results. So this is actually pretty cool that we are able to use error mitigation strategies like this. Again, there is always a price. You have to do more measurements. You have to run more circuits, but more circuits versus a deeper circuits with poor results is not what you want. So let me then close. I'm a little bit over time, I see. This is really not a small team of people that have developed a lot of the things that I talked about. On the physics side, there is a lot of work from my group, high energy physics group, the nuclear physics group. There's a lot of teamwork on dealing with error mitigation, and I should not say these things are orthogonal. This is actually a real multidisciplinary interaction. We have mathematicians in our team, and we have computer scientists really working on compiler frameworks to make these things happen. And rest me to say that this all this work was funded by the Department of Energy's Advanced Scientific Computing Research. And we actually used a considerable amount of time at the computing facilities that are available to really do the compilation, for example. And if you want to read more, you can take a look at some of the websites. Our main one is the AIDE-QC.org, which is our big effort with about 6 national labs and a couple of universities to really develop a quantum computing software stack for this field. But it also involves high energy physics and nuclear physics. And for that, I'll leave it with that, and thank you for listening.
Okay, thank you very much.
Yes. I mean, we still have time for questions. If people want to ask questions, they can they can raise their hand.
There is one question by Felix. Okay, can you unmute yourself?
Yeah. Hi, Bert. Thanks
Hi,
for the nice overview. That's very interesting. I had a quick question about something you mentioned at the beginning. I hope you can hear me well. I have very bad Wi-Fi connection today. You mentioned these barren plateaus in this VQE, right? And that they are NP hard. How should I think of those, right? Is it making VQE kind of like useless, or does it depend sort of on the Hamiltonian, you know, that you're trying to optimize, or what does it mean, right? I mean, that seems like a serious problem, right? If that really turns out to be an NP-hard problem, is there a proof of that, or what's sort of the status of this?
I don't think there is a full proof, but there is especially a couple of papers out of Los Alamos around how to try to effectively not solve the problem, but get around it. If you really think about what is happening, first of all, this is going to be Hamiltonian dependent. I think the problem becomes harder and harder when the more strongly correlated your problem is. If you have weak correlation and you have a lot of local interaction, so to speak, it's a little easier to do than the strongly correlated problems. But it's also a challenge of how you effectively represent and discretize your wave function. What we see in especially in some of the fields that the Los Alamos group looked at is that we are over describing our wave function. So we end up also with a lot of linear dependencies effectively in our description, which makes it even harder. But inherently, a lot of interactions when you go to a strongly correlated system are going to be very similar. So again, you kind of end up, to me, this is my sense of it, is you end up with a lot of linear dependencies, right? And you can describe things in many different ways at the same time. And so, yes, it's a tough problem. So what do? They realize that you need to go and find a encoding, a discretization that is minimal. So you see things like adapt VQE come out, for example, where they start with a minimal set and slowly expand till they get the right answer. That way they can, to some extent, hopefully circumvent some of these barren plateaus, these gorges that they see. They have all kinds of terms now to deal with it, but it's a challenge. Is it useless? I don't know. I think where we are right now, we can get away with a lot of problems because truly we're not tackling all the way the strongly correlated problems with VQE. We tend to do still Hamiltonians that are a little bit more weakly correlated, and then we can get away with it in the sense that you can reduce your wave function complexity, or you can localize the interactions and allow it to not run into these kind of barren plateaus problems.
I see. So basically what you're saying is they're rewriting it in some clever way that it's not an NP-hard problem anymore.
Yes.
I see.
Yes.
Okay.
That's what we always do, right? Everything, if you look at it carefully, everything that has been done is trying to rewrite it such that in a clever way. But actually, the interesting part of that is, so we're trying to effectively figure out how we efficiently encode physics. And that's not, we've done that on classical machines, right? On classical computers, we have a Hamiltonian we want to solve. We do some discretization, one way to solve the equation and try to get that in the most optimal way on a classical computer. The same game holds for quantum computers. And the big challenge we have, I think, when it comes to the field of quantum computing is the first reaction, gut reaction that we have taken is say, okay, we want to solve this Hamiltonian. We know how to do it on a classical computer. Let's try mimic this on a quantum computer. Well, that might not be always the most efficient way. And I think in the more recent years, people have been realizing that and really starting to approach this in a slightly different way, where they're really starting to rethink the problem from the basics. Here's my Hamiltonian. What would be the best way to really try and solve this utilizing a quantum computer instead of thinking, how did I do this on a classical computer before?
Mm-hmm. I see. Okay, yeah, that's very, very interesting. Thank you.
Okay. So Mayan can ask no question.
Hi, thank you for the nice review talk. So when you talk about the open quantum system, so there are qubits for the system, and you also mentioned the ancillas for the environment. So I'm not familiar with this ancilla and the qubit. So what are the difference between the ancilla bit and the qubit? And also,
yeah, I might have confused you there. So all of these are qubits. I should have, what we do when I use the word ancilla, but it's not really an ancilla. It's just another qubit. It's just a qubit that represents the environment. But what we know we have to do with different time steps is we have to do a reset of that environment. And to be able to reset that the qubit environment qubit, we can only do that right now at the end of the simulation. Well, we have been able to do that only at the end of the simulation. So that means we now have to add qubits. And that's why I showed you the having to do 4 qubits for the environment, even though we only preferably only needed 1. This actually now is different, right? So the ancillas is not the right terminology here when it comes to the environment. So I'm sorry I confused you there. It's just another set of qubits.
Okay, thank you very much.
Okay, now I don't know if there are more answers, more questions. Since we already essentially used all the time for the questions and for the break, we can move to the discussion.
Yes, let's